Here's a recap of all of the different measures of variation that we've gone over in this chapter. We started with the range, and if I'm going to give a few important points about the range, first I would say that it was easy to calculate, and it was definitely easy to understand. So it's got that going for it. However, there's a couple of points that come up right away that didn't work in favor of the range. They basically are the reason we don't use the range very much. The first one was that the range doesn't use all of the data that we've collected. Remember, it only looked at the difference between the highest and the lowest value. So that's not really what we want to strive for in statistics. We're not trying to ignore most of our data. Also, if one of those values, like the lowest point or the highest point, if one of them was an extreme score, like if, let's say, we had 1, 3, 5, 5, and then the highest number was 182, well, there's a huge range between the lowest and the highest, even though most of our data is clustered close together. So even though we don't really have very much variation in most of our distribution, a single extreme score can take the range and inflate it to a very large number. So I would say that the range is too sensitive to extreme data. It doesn't have to be extremely high. It could be that most of the numbers were high and one of them is extremely low. So that was the range. Now the next one that we encounter, let me clear some space here. Sorry about that. The next one we came across was the deviation. Deviation, and I'll just put in brackets here, that means deviation from the mean. Now, a deviation literally just means the difference or the distance. So I'll say it's the distance between a single value, so a single data point or a single score, and the mean. So let's say, for instance, again, I'm just making up my example here. Let's say, for instance, you were told that the average height for females was, I don't know, 5'8". Maybe that's too tall. I'm not sure. But you are 5'9". This means that you are 1 inch above average. You have a deviation of 1 inch. Okay, so bad example. That's probably way off from actual heights, but anyways, that's what a deviation means. It's how far you are from the mean. And the way that we calculate that is like this. A deviation is equals to the difference between a score and the mean. And there's going to be one, oops, let me say it like this. I'll say that there is one deviation for every score. Now, because there's one deviation for every score, this doesn't really help us to summarize things. If we have 1,000 scores, if we have 1,000 pieces of data in our sample, then we're going to have 1,000 deviations. So the deviation is not the best measure of variability, simply because there's going to be just as many of them as there will be data points. We need to have a single value that sums up all of the deviations. So what we tried to do is to find an average of all of the deviations. So I'm going to put that here, the average deviation. Now, the average deviation is not really something that we use in statistics. It was just an idea that would have worked, or it makes sense, but it didn't actually work out. And I cover that in my video where I talk about the variance and the standard deviation. But the average deviation was just the idea that we need to summarize all these deviations. Because we have so many of them, there's going to be as many deviations as there are data points. So an average deviation looks like this. It would be the average deviation. When you want an average, you take the sum of your deviations, the thing you're trying to average, you have to take the sum of all of them, over the number of deviations. And remember, I said it's going to be n. It's going to be equals to the sample size, because you'll have one deviation for every observation in your sample, every participant in your sample. Now, that seemed great. It works out. It's easy to calculate deviations, so we just do a bunch of those calculations, add them all up, sum them up, and then divide by n. However, the problem was that it always sums to 0. That was because the negatives cancel with the positives. That's my way of writing positives. Okay, so for that reason, the average deviation did not work as a concept. So it died when we realized that it always sums to 0. 0 should mean 0. If we get a measure of 0, that should mean that there is 0 variation. But I gave examples. I went through some examples where I showed that we always get a 0 for an average deviation no matter which data we use. So the average deviation doesn't work at all. Because the average deviation doesn't work, that means that deviations themselves are kind of a bad choice. If we have too many deviations, if we have a whole list of deviations, what are we going to do with them if we can't take their average? Well, this was the problem. The negatives cancel with the positives. There's a way when negatives are creating a problem for you. If the negatives create a problem, you can get rid of them by squaring your values. So instead of taking deviations, we're going to take squared deviations. So let's talk about that. This is where the variance comes in. The variance is the average squared deviation. Now, why would we do this? Well, when you square any quantity, so let's say you take a number like -2, you square it, -2 times -2 equals +4. If you have a +2 and you square that, +2 times +2 equals +4. So squaring things has that sort of magical property where it takes any value and makes sure that it's positive. If you have nothing but a list of positive numbers, so if all of your deviations are positive because you squared them all, none of them will cancel each other out. So you're going to be able to take the average. So that's what the variance is. Variance is the average squared deviation. We do that only because our answers otherwise our average deviation would always come out to be 0, which is kind of useless. So the variance works. It gives us a number that's not always 0. Okay, so this ends up being a good measure of variation or variability, however you want to talk about it. The reason for that is it's not going to be 0 always, unless the scores truly are constant, truly have no variability. So unless the scores are all the same. So if you do get a 0, it means that you're actually witnessing a data set with 0 variation. That means whatever answer we get is going to allows us to compare different distributions. As the variance goes, if the variance goes up, that means that variability variation has also gone up. If the variance is a lower number, that means that there is less variation. So this is a good measure. Variance works for us. However, it has its own problem. When you square quantities, that means that your actual number is larger. Look at over here. Let's say we wanted to get rid of negatives, so we square all of our values. Well, you take a -2 and you square it, it's no longer negative. That's true. However, the number itself is also much larger. 4 is twice the size of 2. What if I squared a number like -20? Well, -20 squared is positive 400. That's not twice the size. That's like 20 times the size. So when you square things, you end up getting very inflated results. So the last thing I'd have to say about variance is not an intuitive measure. What I mean by that is just hearing the number doesn't really tell you in an easy to understand way what's going on with the variation. So it's not an intuitive measure. It's too large. Also, the units are squared. If we were measuring dollars, the variance would be in squared dollars. If we were measuring height, the variance would be measured in squared centimeters or squared meters or squared inches. So it's a very confusing kind of concept. Now, variance is used in statistics quite a bit. However, if you want to talk to people about variation in a very straightforward way that can be easily understood, at least in terms of the result that you give them, that's where you have to move to the standard deviation. So the standard deviation takes the variance and it takes the square root of it. Actually, let me take a second and just point out that this relationship, the standard deviation is equals to the root of the variance, is an important relationship that is going to stay true throughout the entire course. The reason I have to make a point about that is that our formula for finding variance looks like this. The variance is equals to the sum of squared deviations, shortened to be called the sum of squares. Oops, that's a funny looking S. The sum of squares. It's the sum of your squared deviations over n. This is our formula for variance, or at least this is the formula for variance now in this chapter when you're first introduced to variance. You're going to encounter a little bit later on within this first chapter where you look at variability another 2 or 3 ways to find variance. There's going to be another method for populations to find variance. There's going to be a couple more methods introduced after that to find variance when you're dealing with sample data. So you're going to have lots of different formulas for variance. But no matter how you find the variance, and actually there's going to be even more formulas in later chapters, you probably end up with about 7 or 8 or 9 different ways to find the variance. So you have to remember a lot of them, or you're going to have cheat sheets where a lot of these different formulas are recorded. However, once you found the variance, getting to the standard deviation always happens the same way. No matter how you got to your variance value, you just take the square root. That gives you your standard deviation. The whole point of the standard deviation is to correct that one problem with the variance, that the numbers are inflated. They're too large. So by taking the square root, you're effectively trying to undo that squaring. And so you get a smaller number, and that's what the standard deviation is. In fact, the standard deviation can be thought of as being what we were after in the first place, the average deviation. Now, it's not technically an average. To find an average, what you're supposed to do is you're supposed to find a sum. So that would be the sum of your deviations over n. We couldn't do that. That's what an average deviation would actually be, and that was always equals to 0. So that one didn't work out. But we find a trick. what we do is we square our deviations. So it's the sum of the squared deviations. But now that we've squared things, we take the square root. And this is how you find the standard deviation. The standard deviation is like a trick that we pulled to get to what we really wanted, which was the average deviation. On average, how much do the scores deviate from the mean? So that's how I would think about the standard deviation. On average, how much do the scores deviate from the mean? Okay, so those are all of our different measures of variation. We started off with really simple, the range, and worked our way up to something fairly complicated, the standard deviation. But it was trying to accomplish something that I think also is fairly straightforward, an average deviation, which normally turns out to be 0, but we found a couple of tricks. We squared things to get rid of the negatives. We took the square root to bring the numbers back down to a manageable size. So that's it for concepts in this chapter. In a later video, I'm going to have a look at all of the different formulas for expressing these ideas for variance and standard deviation. I almost forgot to mention one really important thing about all of the measures of variation that you're going to end up using. So by this I'm talking about the range, and I'm talking about the variance and the standard deviation. I'm leaving out deviations, so not deviations. I'll explain why in a moment. The range, and I'm also actually leaving out the average deviation because that's not a real thing. That's something that we wanted to be able to do, but it was always equals to 0, so it's a completely useless measure that we avoid. So the range, the variance, and the standard deviation, those cannot be negative. It's very important. There's going to be times where you're doing calculations and you're probably going to make a mathematical mistake here and there, but one of the ways you can determine that you've done something wrong is if you get a negative result. These things, range, variance, and standard deviation, they measure how much variation there is. Well, the smallest amount of variation would be 0. 0 means there is no variation. And that can go up to, who knows how large that can go. That can go as large as the numbers are that you're dealing with. I guess technically this could go up to infinity. So that would be lots of variation. So there is nothing less than no variation. You cannot get a negative result for range, for variance, for standard deviation. Now the reason that deviations from the mean, so the reason that x minus the mean is excluded from that rule, that they cannot be negative, is because it's entirely possible that you can be below the mean. So let's say that, well, I did an example earlier where I had a company A, had a salary or an average salary of $50,000. And we took a sample of people from that company, and somebody was making 30, somebody was making 40. So these were my X values. Somebody was making 50, 60, and 70. So the first couple of values here, $30,000 and $40,000, those are less than $50,000. So when we look at deviations, they can be negative. So 30, so that's the x is 30, minus the mean, which is 50. 30 minus 50 is negative 20. The negative here is fine. It just means that we're below the average. An individual score can be below the average because deviations do not measure variation in the entire group. They only measure how far a single value is away from the mean, and negatives are used to show that you're below the mean. So you can have negatives, meaning that you're below the mean. You could have positives, meaning that you're above the mean. Or you could have a 0, neither negative or positive, showing that you're right at the mean. This value of x is exactly the same as the average. So your other measures of variation, the range, the variance, and the standard deviation, as they're introduced in this chapter or in any chapter to come, cannot be negative because it makes no sense. You can't have anything less than no variation.